Good morning. We're studying Chapter 8, and we're going through complex numbers. This is a lead up to being able to solve AC problems. So basically there's a purpose behind this, and it's, while it may not be obvious to you right away, you will see that as we go through this, there's a reason for what we're doing. So if you wanted to go between Toledo and Cincinnati, you would just say it's 200 miles, and you just go down I-75, and that's the only way to get there. However, if you're going to go to Indianapolis, if you're going to try to describe how you go to Indianapolis, you could say either that you could go down I-75 to Dayton and then turn right and then go over that way, or you could go down US 24 to Fort Wayne and then follow I-69 down and go that way. So in this situation, you have not only mileage, but you have direction, and those are two ways of getting there, and you can decide which way you want to go. But basically, there is a direction involved as well as the number of miles. So we describe numbers in the same way, or we describe units of quantities like voltage and current in the same way. Up until now, we just dealt with simple scalar numbers, and later on we're going to be jumping into circuits with more complex numbers, which include direction. So if you have a battery, we just add the numbers up around a loop and solve the equation. When you delve into sinusoidal waveforms, however, the quantities may be simple or they may be complex, depending on the devices in the circuit. We need to learn with complex numbers if you need to look at it with with complex numbers, or with just simple scalar numbers. So anytime you add an inductor or a capacitor, you're going to jump over into complex numbers. So that's what we're looking for. AC with complex numbers is with AC with an inductor or capacitor. So you have to check that out and see which way that is. So again, we're no longer in Kansas, Dorothy, and that's to say it mildly. Here we're looking at a number, and it's just a scalar number, but it also has direction. It has magnitude 10, but it also has direction of 0 degrees. Here we're looking at the same number, magnitude 10, but at an angle of 180 degrees. So we would describe this number differently than we would this number. Here's one at angle of 60 degrees with an angle of 60, magnitude of 6, but with an angle of 50 degrees. Here is one with a magnitude of 5, but with a direction or an angle of minus 40 degrees. So a vector, which is what these are, have both magnitude and direction, and is similar in a Cartesian plane to following the vector compass. Okay. So here is our vector compass, and we can look at an AC waveform, and we can see that this one is ahead of this one, or it leads it by an amount. And if you look at this, if you were to look at our lab number 9, you would see this exact same thing. You would see the leading of one waveform with another. So if you have a phase shift, we would say something like this. If we have a phase shift of 135 degrees, we would see a phasor similar to the following. Here would be our original one, and here would be our phase shift of 135 degrees. So if we do have a shift, it's measured in degrees, and it's measured with respect to the peak, or it could be with respect to where they cut through the x-axis. Either way works. So here would be a waveform where A leads B by 90 degrees. A is at its peak, while B is just starting up from 0. So the difference between this peak and this peak is 90 degrees. So when this one's going from its peak to 0, it's when this one's at its peak. So when it goes from its peak to 0, this one is at its peak. So that's a 90-degree change. Here's one where B leads A by 90 degrees. Here's where they're exactly out of phase with each other. A is going up while B is going down. They're exactly the opposite. Here's one where they're exactly in phase, and they're laying on top of each other, and that would be both of them looking like right on top of each other. So when we're talking about phasors, we're assuming that the waveforms are all at the same frequency. This is implied, and if they're not, this all falls apart, but they usually are. We usually don't reference frequency, we just reference the phase angle or the difference in where they are with respect to each other, and we assume that they're all at the same phase. Now here's an analogy that you may or may not think about, but if you've ever been to a dog track and you've ever seen dogs racing, here's what happens. The dogs are running to chase the rabbit. If they ever catch the rabbit, the race is over, but they never do. So as really, these are all dogs running to try to catch this rabbit. So here's the rabbit. Here's dog 1 and here's dog 2, and they're all running around this loop, hopefully at the same speed, but the rabbit is always ahead. It's always going to lead. Okay, so the dogs are they're out of phase with the rabbit. Another way of looking at phasors is looking at a clock with the hands moving backwards, counterclockwise. The eyes move, the tails move, and the hands move backwards. Only those. This is not a true clock because this clock would be going clockwise. But in the phasor diagram, the hands actually move backwards. So if you're trying to picture a phasor, picture it as a dog track, or picture it as a cat whose hands move backwards. Okay, so now we're going to concentrate on the math part of this. And again, the waveform has amplitude. It also has frequency, but we pretty much ignore the frequency because they're all the same. So we're looking at the amplitude. Okay. And if we were to add two voltage supplies that have, one has a waveform of 6 volts at angle of 0 degrees, and one has a value of 10 volts at angle 60 degrees, you can't add them the same way you do battery supplies. Here, with V, you just add them. 6 and 10 is 16. But here, you have to look at them as phasors and solve them graphically. So you would have to add the 6 and the 10 to get you a vector that is, here you would measure, it's not 16, it's 14. And it would have a phase angle with respect to the 6 of 38 degrees. But if you were to measure it with a voltmeter, you would not measure 16 volts, you would measure 14 volts. Very different situation. This leads us to the subject of complex vector addition. So, to add two vectors, we simply add the x component and the y component and find the resultant vector. For the 6 at 0 degrees, there is only an x component of 6. For the 10 at 60 degrees, the x component is 5 and the y component is 8.66. Therefore, we say 6 plus 5 is 11, and for the y we get 8.66. Now we find the resultant vector. It is 14 at angle 38.21 degrees. We use polar notation for complex numbers to find the sum of these vectors. In order to work with complex numbers without drawing vectors, we first need some kind of standard mathematical notation. There are two. One is polar and one is rectangular. Okay, so you have two representations, either polar or rectangular. And for looking at a sine wave, here would be the magnitude, and here would be the time dependent. This is the time varying signal, and this is the phase shift part of it. This would be the phi, or the second part would be the phase shift part, and that's the one we concentrate on. So here is the phi, or the angle. This would be leading. Now this would be at an angle of leading. Here would be the phi angle right here, and the value of the magnitude, the I, is this peak value times 0.707, and you've heard of 0.707 before. So you always represent this as RMS current at an angle phi. So you look at this part up here, the phi, and you bring that down here, and that becomes this part of it, and the I, as you divide the peak by 0.707, or you multiply by 0.707, divide by 1.414. So these are variable numbers, and you have, this would be my magnitude, would be my RMS value, and my RMS value. Okay, so here we look now to convert from polar to rectangular, because you know that polar is useful for multiplication and division, but rectangular is useful for addition and subtraction. So you have to be able to go back and forth. So how do you do that? Well, in a calculator, 4 plus J3, you enter the 4, then the R to P, then the 3, and then the equal, and the resultant is 5. You do that in a standard calculator, that's what you're going to get. And then the X to Y, and you get the 36.869, or the degrees. So then you can write 4 plus J3 equals 5 at angle 36.869 degrees. That's rectangular to polar. Okay. So, and polar to rectangular is just the opposite. Now, we can add complex numbers, we can subtract complex numbers, we can multiply complex numbers, and we can divide complex numbers. Addition and subtraction is done best using rectangular format. So if I add two numbers, it's best to add the rectangular in rectangular format. So I have 2 plus J5 plus 4 minus J3 is 6. You add the reals, and then you add the imaginaries. Now the J we use instead of I. Why do we use that? Well, because I is reserved for current. So in electrical jargon, we say J instead of I for an imaginary number. So it's J. Okay, so this is the imaginary part. This is the real part. So we come down here with a real and imaginary part. Subtraction, we do the same thing. Multiplication, we use polar, and we say 35 times 10. So we multiply the real times the real, and then we add the degrees. So we say 65 minus 10 is, that should be 55 instead of 53. That's a typo. So we multiply the magnitudes, we add the degrees. Division is done a little differently, and it is 35 divided by 10, and it's 65 minus 10, or that's a typo again. That should be 65 minus 10, or 55. So this should be 55, and that should be 55 as well. So that's a little bit of an error. Okay, now here's where it gets kind of confusing. If I were to pick up a voltmeter and I were to measure across a DC supply, I would have to get my leads right in order to measure plus and minus. So if I did it one way, it would be plus. If I did it the other way, it would be minus. So that's a thing you always just have to think about, pluses and minuses with DC. But with AC, if you did the same thing, you would say, okay, there would be no sign. With AC, the polarity drops off, and you just say 6 volts. So here's another way of looking at representation of a bunch of waveforms, which is what you're kind of looking at here. Okay, so this would be the resultant torque of an 8-cylinder engine. So here would be the first cylinder's contribution, the second cylinder's contribution, the third, the fourth, the fifth, the sixth, the seventh, and eighth, and then back to the first again. So they actually fire 1, 5, 4, 2, 6, 3, 7, and 8. So that's how they fire. So here would be the first one, the contribution, and here would be your resultant. So if you were to add vectors and you'd say, how do I do that? This would be your resultant vector for each of these all going at the same time. If that's confusing, don't worry about it. But that gives you a little bit of an idea that this is not only an electrical phenomenon, it's a phenomenon you see throughout nature. Okay. So here is some more. We're going to be talking about circuits, some examples with AC circuits. And here I want to add these circuits, these three voltage supplies together and get a single supply. So if I measured these are AC sine waves. If I measured this, would measure 22, this would measure 12, this would measure 15. If I measured across the whole thing, what would I get? You would get the vector summation of those supplies. Okay? Your answer would be the resultant right here. And you build it by adding the real and the imaginary parts. And here would be your answer, 36 at angle minus 20.5. So if I measure those voltages independently, I would see these voltages out here. But if I measured across the whole bunch, I would get this number right here. Now, if you flip the leads on one of them, what have you done? You've changed the number here from a minus to a plus. And in that case, what did you do? You turned the vector around, didn't you? And your answer is going to change. Okay, now we'll start up with the next section with the problems, and we'll work through some of these problems. Take care. Hi, we're working on problems now at the end of chapter 8, and so the goal here is not to just do every problem, but to do some of the problems, and we're just going to go through these one at a time, and we'll see what we got. So we're going to work with first few here and see where we're at. So hang on a second, we'll get our sketch pad up and we'll work on these as we can. Okay, so we're going to transfer over, and we're going to look at the sketch pad now, and we're going to start with some of these early problems, and we'll see where we're at. Okay, so the first one there is to convert each of the from rectangular to polar. So the first one we're going to look at is number A, 8-1A is 2 plus J5. So on my calculator, I have a R to P, and that's what we need to do. So I hit 2 R to P 5 equals, and I come up with the answer of 5.385, and there's an angle, so I hit the X to Y conversion at 68.19 degrees. And that's how I do it. Okay, so you can do the next one. Minus 3 plus J6 equals, get the 3 with a minus sign, R to P 6 equals 6.708, X to Y 116 degrees, 116.56, Ted. And that's our answer. And I'm going to let you do the rest of them, okay? And also for number 2, I'm going to let you do those as well, because they're pretty straightforward, but I want you to be able to do small numbers and also large numbers. Now number 3, let's go to number 3. Four at an angle 60 degrees. This is going to be P to R, polar rectangular. So I hit 4, shift P to R, then I hit the 60, then hit equals. Okay, so here is my answer. It's 2 plus J 3.464. Okay. Next one, 7 angle 130. So I hit the 7. P to R 130 equals, so it's minus 4.499 plus J 5.36. 5.362. Let you do some more of those. So now number 4 shows some of these in polar and rectangular format. So let me just do one of those, 8.1. So I'm going to do 8.4. But I'll do the 2 plus J5. Okay, so let's draw the vector. So here's the 2, and here's the 5. So it's like this. It's at an angle about 60 degrees. So here's my 2 in the x direction, 5 in the y direction, and here's my final answer. Not very pretty, but that's the idea. Okay, so you can do the rest of those. Number 5. So now we want to add two numbers. So 8.5 A, 2 plus J 5 plus a minus 3 plus J 6. So the answer here is minus 1 plus J 11. You add straight down. It says then subtract. So at 2 plus J 5 minus a minus 3 plus J 6. So it's 2 minus a minus 3, or 5. J5 minus J6 is minus J1. For multiplication, you really have to convert these to their polar format. So 2 plus J5, let's go back and do it again. 2 So 2 plus J5 is equal to 5.38 angle 68.19. The 3 plus J1 minus 3. Okay. .708. An angle. Of 16.56. So if I multiply 5.38 at angle 68.19 times 6.708 at angle 116.56, I multiply the magnitudes. 5.38 times 6.708, that gives me 36.089, and then an angle of 68.19 plus 116.56, or 184.75. So that's my answer for the multiplication. The division is 5.38 at angle 68.19 over 6.708 at angle 116.56. So this one is 5.38 divided by 6.708, or 0.802, at angle 68.19 minus 116.56, or minus 48.37. So here's my multiplication, here's my division, here's my addition, here's my subtraction. Okay, so that gives you an example, and then you can follow through with that. Okay. Now let's go down to 8. So now we're given the whole problem. Okay, 8-8. 7 plus J12 over 42 minus J12. Okay, so now we're presented with a problem. We have to do the conversions ourselves. So it's 7 plus J12 to polar. 7, 12 equals 13.89 at angle 59.74. The denominator, 42, .68 at an angle minus 15.94. So it's 13.89 divided by 43.68, or 0.317. And then the angle is 59.74 plus 15.94, or 75.68. So there's our answer. And I'll let you do the rest of them. But those are all very doable, and just takes time and practice to do them. Okay. So number 9. A sine wave has the following equation. I equals 20 sine theta plus 35 degrees. Find the phasor current. Okay, so here we start. I is equal to 20 sine, and I'm going to write it as omega t because that is what theta is, plus 35 degrees. Okay, so our phase angle is right there, and our peak is right there. So we want to find the peak times 0.707. What is that? 20 times 0.707 equals 14.14 at an angle 35 degrees. And that's the phasor. This is our phasor current. Okay, so that's how you'd write it in phasor notation. So now for the next one, that would be 8-9. So for the next one, 8-10, we have a peak value of 8. So it's 8 times 0.707, 5.656, and then it's an angle leading of 55 degrees. So that is my phasor. And then the last one is 8-11, and that is 20 milliamps. And this is in volts. You can say in volts in this one. You can say amps in this one. And for the last one, it's milliamps. So it is 20 times 0.707. I've already got the answer, 14.14 at angle minus 80 milliamps. So there's my answer for 11. So for 12, we now are looking at a situation where we've got A is 18, that's the peak. And then it says find the equation. Okay, so we've got to find here, we've got to find the period. The B is 2, so A is the peak. A is the peak, and that is for voltage, so we do 18 times 0.707, or 12.72. RMS is equal to 12.726. B is 2 cycles, so it's B is 48 milliseconds, which is 2t. So 1t is equal to 24 milliseconds. F is equal to what? It's 41.7 hertz. So 2 times pi times F is equal to omega. That's what you put in front of the T. So now we've got all the things we need because it's in phase. So voltage is equal to 12.726 sine of 2 pi times 41.67 t, and that's our answer. There is no offset, or there is no phase shift. Okay. So find the power consumed by R1. R1 is the resistor, 120 ohms. So one of the equations for power is V squared over R. And we use this V, so it's 12.726 squared over 120. 12.726 quantity squared divided by 120 equals 1.349 watts. So that's the power consumed in a 120 ohm resistor by that waveform. The next one, we have three sources. One at 12 at angle minus 34, one at 25 at angle 35, and one at 15 at angle 0. You have to add these three. So the only way to add numbers is in rectangular format. So let's go 12 P to R 34 minus equals 9.948 angle minus J 6.71 0. Okay, 25 P to R 35 equals 20.47 0.478 14 plus 14 put a J in front of it, plus J 14.339. 15 at angle 0, just 15. So now I add the 9.948 plus the 20.478 plus 15, that equals 45.426. And now I have my minus 6 plus 14.339 is equal to 7.629. Here's my answer in rectangular, but we need this in polar because you want to measure the value, the magnitude of it. So it's 45. You got to go back. So the magnitude is 46.06 at angle 9.533. So if you measured these three values independently, you would come up with this number. But if you measured it across all three of them together, you'd come up with this number. Okay, that's our problems at the end of Chapter 8. Take care and have a good day.